Good morning, everyone. A very welcome to day 3 of International Conference on Construction, Materials and Structure, ICCMS 2025 at IIT Tirupati. As we convene for the final day of ICCMS 2025, there is a distinct sense of accomplishment. The past 2 days have not only united leading minds from across disciplines, but have also fostered meaningful collaborations and opened new avenues for inquiry. Your enthusiasm and active participation over the past 2 days have truly brought this conference to life. As we step to the final day, we hope you continue to explore new ideas, engage in meaningful conversations, and enjoy every moment. We move on to our plenary sessions. Each participant will have 35 minutes for their presentation, followed by a 5-minute Q&A session. To begin with, we are pleased to welcome Professor Gianluca Ranzi joining us as the plenary chair for this session. Professor Gianluca Ranzi is a distinguished academic and chair of the Center for Advanced Structural Engineering at the University of Sydney. He is internationally recognized for his contributions to the fields of structural engineering, architectural science, building energy management, power demand management, and heritage conservation. Professor Ranzi's research in concrete and composite construction focuses on the development of sustainable structure solution and advancement of modern design guidelines. His work combines theoretical modeling and experimental investigations to understand material behavior and structural performance under both service and ultimate load conditions, with strong emphasis on the assessment and rehabilitation of existing structures. He plays an influential role in shaping industry standards, serving as an active member of numerous Standards Australia and international committees responsible for the formulation of design specifications of concrete and composite structures. Professor Ranzi's outstanding contributions continue to impact both academia and industry, promoting innovation, sustainability, and excellence in structural engineering. It is with great respect and anticipation that we invite Professor Ranzi to take the lead and guide us forward.
Good morning. Thank you for the introduction. And then first of all, good morning to everyone. I hope you enjoyed the dinner last night. It was wonderful. Really big congratulations to the organizers. It's been welcoming. I've been talking to some of the delegates coming from overseas. Everybody feels so warm here in terms of really warm heart. It's a wonderful place to be. And we see a lot of passion all around the place. Let me now introduce you to the first speaker. It's my pleasure to invite Professor Manu Santanam to deliver the first plenary talk of the day. His presentation, titled Decarbonization Approaches for Concrete, Advantages and Limitations, will offer critical insights into one of the most pressing challenges in sustainable construction. And Professor Manu Santanam is the Surendra and Dorothy Shah Chair Professor in the Department of Civil Engineering and currently serves as the Dean of Industrial Consultancy and Sponsored Research at IIT Madras, a fellow of both the Indian National Academy of Engineering and RILEM, and he is widely recognized for his excellence in cement and concrete technology. His pioneering contributions span durability enhancement using supplementary cementing materials, sustainable binder systems, and cutting-edge innovations like 3D concrete printing. His work seamlessly integrates material science and civil engineering, advancing sustainable and performance-driven construction practices. Please join me in welcoming Professor Santanam to the stage, and we look forward to a wonderful presentation. Thank you.
Sure. Okay, great. Okay, thank you for the introduction, Professor Ranzi. It's indeed a pleasure to be here. very impressive lecture hall complex. I was just remarking to my IIT Tirupati colleagues. And of course, it's always a pleasure to come back to IIT Tirupati. It's almost like home for us because many of the faculty in civil engineering at IIT Tirupati have also been with us before at IIT Madras. So it's indeed wonderful to be here. And I'm really delighted to see the kind of participation that we are seeing even on the last day. And yesterday at the gala dinner also, it was really packed and full. And that's very impressive for a conference. So today I'm going to talk about, I didn't intend to talk that loud, but yeah, okay. Yeah. Maybe I should not be near here. Okay. All right. So I'm going to talk about something that has probably been the topic of research in many different universities around the world. People talk about decarbonization of construction. Primarily, we are talking here about concrete construction. Of course, there's a lot of emphasis on decarbonization in steel construction also, but my talk is emphasizing concrete construction. But what we have to look at is the entire picture and understand what are the real advantages and where we really need to do some work to address some of the problems in a scale that is not easy to do in the lab, right? So some limitations also I'll point out on these. So concrete obviously is a much vilified material. Everybody says that concrete causes a lot of greenhouse gas emission, which is not really wrong. Cement production itself is responsible for 6 to 8% of global CO2 emissions. And if you look at the concrete construction process, it's about 20% of global emissions are from concrete construction. And of course, if you combine the operation of buildings also, it can go up to about 40%, the overall CO2 emissions. So we are talking about a real contributor to the global economy of CO2. And that's where a lot of interest has actually sparked a lot of research at different universities to try and find out strategies by which this can be reduced. But if you look at the per kilogram emission and CO2 and energy from concrete, it's actually lower than several other materials like wood, glass, or steel, right? Only problem is we use a lot of concrete. Nearly 25 gigatons or 25 billion tons of concrete is used on an yearly basis, right? So because of the quantity that we use, the impact of concrete is large. And especially in terms of the largest emitter within concrete happens to be cement, and that's about 4 to 4.5 billion tons in a year. So that's a significant quantity of cement that is being produced. A lot of concrete is being used. So definitely the impact is going to be huge. And much of the CO2, as I said, is attributable to cement. Of course, building without concrete is not possible in today's world. We know that concrete is a material that we are familiar with, that we are comfortable with using. So building without it is something which is not conceivable today, right? So what do we do? How do we lower the impact of concrete? One thing is obviously to use less of concrete. Now, is this possible? Of course, you will have to go into the realm of structural design. We are not talking from the material characteristic perspective, but more from structural design. Can we optimize structures to reduce the amount of material that goes into making the structures? So that's obviously the only way out there, right? A lot of strategies in Western countries has now moved towards adopting earth-based construction, right? Because earth obviously is a lot more sustainable as compared to produced material like concrete. Unfortunately, when we talk about longevity, when we talk about durability and resistance to the atmospheric effects, concrete happens to be an excellent material. And that's why it's mostly favored, where people could actually look at other options, but really speaking, they are not really there in the scale that we want to construct. Then the second aspect is, since cement is the main contributor, can we reduce the CO2 impact of cement by using alternative fuels, which will emit less CO2? The other one is reduce the cement consumption in concrete. Reduce cement by using appropriate supplementary materials. And this is something that the whole world agrees upon as being the single most important strategy as far as reduction of cement in concrete is concerned. Then we have alternative cements, which are developing to some extent, but they are hampered by the fact that the raw materials that go into manufacturing alternative cements are not that easily available. The magnesium-based cements, for instance, happen to be carbon absorbers. And so net carbon dioxide emission is on the negative side for the magnesium-based cements. But getting there involves a lot of different processes. And very often, if you take in totality, maybe the signature of the magnesium cements also would be negative as compared to ordinary Portland cement. The use of recycled concrete and industrial waste for aggregate, that's an absolute must if we have to reduce the impact of concrete, because relying on natural resources, denuding natural resources is going to be a challenge for us. We are not going to be able to find right quantity and quality of aggregate anymore. And recycling concrete or demolished concrete is absolutely going to be a necessity for the future. Again, that will help us reduce the overall burden on the natural resources. CO2 curing and CO2 sequestration within concrete, these are aspects that are sparking a lot of interest. I mean, I don't know how many startups have actually developed with this kind of an approach, talking about putting CO2 into concrete or curing concrete in a carbon dioxide intensive environment. That changes the chemistry a little bit. What we are trying to do is induce carbonation in your concrete system at an early stage where you don't expect that to affect your reinforcement, but we don't know what will happen in the long term because these are all fairly new studies. But since a lot of concrete in the world is unreinforced, this could be a valid utilization of the technology for unreinforced concrete. With reinforcement, with structural concrete, we have to pay a lot more attention to what's going to happen in the long term. And we can also look at repurposing older concrete elements wherever possible. Because again, there's no point in actually taking older concrete structures and demolishing to make aggregate all the time. But there may be some instances where the structural elements that we extract from buildings are in a condition that can be repurposed and reused in new construction. Now, the only challenge there would be that you need to start thinking about designing the structure with that perspective in mind. You need to design for deconstruction. We know very well that it's not very easy to remove entire elements which are perfectly, which have a full dimension and reuse them in new structures. So how do we design for deconstruction? Can we look at strategies by which we can remove concrete elements at the end of life? The end of life could not have been because of that element. Maybe something else caused the end of life for that particular structure. But can we remove these elements? Much like your Lego blocks, right? You have your Lego blocks, you put them up in certain shapes and sizes, and then you can actually remove the Lego blocks to get the pieces back again, reassemble in a different form. And most important, obviously, if you want to really reduce the impact of concrete, is use it in such a way that it lasts for very long. In other words, make structures durable. If you make structures durable, you don't have to repair or replace structures very early. You have a longer life, and that makes your overall, the net footprint over the life cycle of the concrete structure can be reduced. Now, let's look at some of these topics and understand what are some limitations which are bogging these down. For instance, alternative fuels. What are the options for alternative fuels? We have petroleum coke or pet coke. This is already being used in a big way by cement plants. It reduces dependence on coal, but the only problem is it's even worse in terms of emissions, right? So while we are reducing natural resources like coal, but petroleum coke, again, is something which induces very large amount of emissions. The other aspect is municipal solid waste. It reduces fossil fuel dependence, but again, the emissions are difficult to control. I don't know if you recall, sometime back, the Maggi noodles was pulled out from the market, right? At that time, most of the discarded Maggi went into cement plants as fuel for our kilns, right? So again, if you look at cement plants, they are really optimizing the use of alternative materials quite well. They are actually utilizing waste from a lot of different sources. And municipal solid waste is a possibility there. Again, but there's no control because you get all kinds of mixtures of waste. So you can't really control the emissions well enough. Electrical kilns are, again, being proposed. Hydrogen, green hydrogen for electrifying kilns is also being proposed. The only difficulty there is you're pushing the CO2 burden to a different process, right? Instead of the CO2 because of the burning of the fuel, you're now pushing the CO2 for the burning of coal to produce that electricity and driving the kiln with that electricity. So you're pushing the CO2 burden to a different process. So you need to evaluate that very closely. And again, as I said, green hydrogen, but realistically, to make green hydrogen, that is basically green hydrogen is from the electrolysis of water, right? So that you don't release any other gases into the atmosphere. So green hydrogen is something that will become a reality only when the cost of per kilogram of hydrogen is coming to a reasonable amount. Right now, in some countries, they've achieved certain levels of economy with what they call as brown hydrogen, which is not entirely from a emission-free process, but they have had some success in bringing down the cost of hydrogen. But this is something which is a subject of avid research. A lot of people are looking at how to produce green hydrogen in an economical manner. Now, the other development is using calcium carbonate as a source for calcium oxide. But unlike in the regular cement manufacture process where we burn it at temperatures that release the CO2, can we have some electrochemical processes that can extract calcium oxide from CaCO3? So that's something which has also sparked off some interesting research around the world. Okay, but again, the question will come: is this process itself green? Is this process itself reducing the overall emissions, or does it need so much energy that you are anyway going to be emitting? So again, when we take up any of these research topics, especially to the students, we need to evaluate holistically what should be the overall impact. Because there may be one thing that you're doing that looks greener, but then you have another thing that basically could make the entire process completely negative. So let's look at, of course, the second topic, that is supplementary cementitious materials. This is, as I said, accepted worldwide as the best way to actually reduce the impact of cement. Now, we have to, of course, pay attention to what is available in terms of SCMs. It turns out that many of the SCMs are either available in large quantities, but are difficult to get to, or they are available in small quantities and will not really serve the needs of the future generations. So what are we primarily talking about, at least in India, when we talk about SCMs? We are primarily interested in fly ash, right? Oops. Okay. Anyway, fly ash, you all know very well, India's dependence on coal-powered power plants is not going to go down anytime soon. Our power demands are too high. Currently, our power generation from coal-fired plants is nearly 75% of the overall power in the country. So it'll take some time for that to come down. But until then, we have the fly ash available. Only problem with it is of variable quality. There's a lot of variability in the fly ash quality. So only some of it can be processed and obtained to a quality which is consistent for cement production or for concrete production. So you need to be aware that not all fly ashes will give you consistent performance. You need to ensure that the physical and chemical characteristics are controlled. And that's not something which can be done for free. That has an associated cost. So there are companies which are now selling processed fly ash. And that is something which should develop a little bit more for us to really utilize fully the potential of all the fly ashes that are currently available in the country. The other possibility for us is, of course, slag, but that again depends on how much iron and steel production is happening. In some countries, they've entirely given up new blast furnaces. For instance, in the US, new blast furnaces are almost extinct now. They are relying more on scrap steel and recycling the steel for new steel production. So as a result, since blast furnaces are down, there's no real sources of slag available anymore. This is happening in a lot of countries which want to cut down the production and enable a lot more sustainability in steel manufacture by doing recycling scrap steel. Now, again, that is also a part of the process in our country, but we still have a long way to go before the emissions from CO2 from steel production can be cut down. The other possibility, of course, is clay-based systems like metakaolin, where you burn kaolinite clay at a temperature that induces reactivity. But then metakaolin need not be the only possibility. That means very high purity kaolin is not always needed. The research that we've done for several years on limestone calcined clay cement has shown that we can work with much lower grades of calcined clay, which are perhaps overburdened in kaolinite mines and available in very large quantities and not really usable where kaolinite is needed, because they need a very white kind of clay. So this is mixed clay, which has red, brown, or yellow colors. And that is not suitable for semiconductor or paint or paper industry. So that's a lot of source for calcined clay that is available. But then we don't really know how much of it is there. We need to do a lot more prospecting and find out how much quantity is realistically available for utilization in concrete purposes. Now, of course, limestone is the ingredient that goes to manufacture Portland cement. Interestingly, in the country, there is a significantly large amount of limestone available for cement production. But it turns out only about 8% of what is available can actually be mined for cement production. And among this 8%, you always extract a lot of other material from limestone mines, which is not of the right purity to be used in cement production. So there's a lot of low-grade limestone available at these mines, which could potentially also be a resource for your supplementary materials. So that's where we need to also pay attention to. Why do we need to do all this? It's been estimated that, at least in India, if we utilize all the available limestone to only produce Portland cement, then our limestone reserves, which are good for cement manufacture, may not last beyond 50 years. So you have to look at finding replacement materials, and that's probably the best way to think about why we need to replace cement. And of course, in terms of a sustainability perspective, use of mineral additives is definitely a positive thing, because you are reducing the utilization of cement clinker, which leads to a lot of CO2 emissions. You're utilizing waste from other industries. You are also having an impact on the long-term durability. So net cost over a life cycle comes down. There's reduced potential for damage and deterioration in the long term, except in certain circumstances. So smart thinking would be only to use blended cements and not use ordinary Portland cement as all. I think there are a lot of structural engineers here. You need to really take that step and promote only blended cements. No more relying on OPC. Please ban the use of ordinary Portland cement. You have to use only blended cement. We have to work with blended cement because that's the best way to cut down CO2 emissions from OPC. And if we work with blended cements, whatever be the shortcomings in certain exposure environments, we need to find ways to overcome that by smart design. Those tools for designing concrete are today available. So we have, of course, different types of binders. We need to realize what can perform where. So, of course, we have the latent hydraulic binders like slag, which have a fairly good amount of calcium to silicon ratio, which causes activity if you have some sort of a activation done using an alkali or a sulfate. But then you have pozzolanic materials, which are mostly rich in silica, and that silica has to be in the amorphous form. So there you have a deficiency of calcium. So you need some sort of a lime-based system, either lime produced from cement hydration or lime added onto the system to induce reactivity in the pozzolanic material. So depending upon the composition of the material that you have as a mineral additive, you can have different kinds of chemistries exhibited by these materials. Now, what about concrete durability with supplementary materials? This is part of some research work that we had done, comparing the performance of concrete with ordinary Portland cement to concrete with 30% fly ash replaced cement, and then limestone calcined clay cement. So this was from an industrial production of limestone calcined clay cement that was undertaken by one of our cement companies. And you can clearly see here in terms of your resistivity. So resistivity is a durability parameter that directly links to how disconnected the pore systems are. So the higher the resistivity, the better the durability, right? So here you see, even for a concrete which is of a residential grade, like 30 megapascals concrete, you have resistivities of LC3, which are an order of magnitude higher than that of OPC. So you do get much lower permeability in the LC3-based systems as compared to OPC. If you look at resistivity development with respect to time, you can see that compared to fly ash-based systems, which eventually develop the same level of resistivity, the LC3-based systems are developing this much faster, obviously because calcined clays are a lot more reactive, and that kind of reduces the overall conductivity of your system and improves the resistivity at an early age. Now, in terms of water absorption rate, again, this is the ASTM test method, which looks at the water absorption in the very early stages. You can clearly see again that the concrete with mineral additives performs much better than the ordinary Portland cement concrete. And if you look at the non-steady state migration coefficient, which is today used to do a lot of durability design in chloride exposure environments, you clearly see that even for low grades of concrete like 30 MPa, your LC3-based systems is able to reduce non-steady state migration coefficient to less than 2 into 10 power minus 12 square meter per second, which is actually an acceptable limit for a very high quality concrete, right? For instance, in the Mumbai Trans-Harbour Tunnel, that was the limit specified for the bridge and tunnel elements. So you can imagine that level of durability. That was a 65, 70 grade concrete. But here, this is a 30 MPa grade concrete, and you're able to get still a very high level of durability. So this goes to show that when mineral additives are used, you have the potential to improve durability, especially in chloride environment, right, at lower levels of structural strength. And you don't always need very high structural strengths. The previous methodology of concrete design was you design for a higher strength, so you also get higher durability. But how high do you want to go in strength? Why do you want to unnecessarily keep increasing your strength, right? Your brittleness also goes up. You have a lot of other problems, autogenous shrinkage, right? All of those things can be avoided by simply looking at mineral additives to increase durability at lower levels of strength. Now, what we also have to look at is the impact through life cycle assessment. So at IIT Madras, we undertook, under Professor Gettu's leadership, we undertook a lot of interesting studies to actually collect the data from cement plants and look at the sustainability impact of utilizing alternative materials. So we were able to attribute all of those different aspects like direct emissions from limestone, fossil fuels, pet coke, alternative fuels, electricity, transportation, and any other CO2 or energy inducing system that comes in the manufacture of the cement process. And with that, we were able to calculate that your blended cements had much lower CO2 emissions overall, like your Portland slag cement, obviously because we are using very high quantity of slag as a cement replacement, is leading to a much lower emission as compared to OPC. Now, it's not enough to just say that you're emitting less. Are you emitting less over a life cycle? Are you also producing durability in the concrete? So that's where we actually combined the emission aspect with the actual durability in different types of exposure environments. So what you have on the right is a graph between an index called apathy index, which means our apathy towards durability, right? That means the higher the apathy index, the poorer is the durability. And there actually it takes into account a durability parameter that links to chloride resistance and normalizes it with respect to the carbon dioxide emissions. On the other hand, on the x-axis, you have the energy intensity factor, which normalizes the strength, normalizes the energy for production of that 1 cubic meter of concrete with 1 megapascal strength. So that's the, so here in one shot, you get strength, you get energy, you get CO2, you get durability. And with this kind of a approach, you're now able to look at the sustainability impact of different types of combinations and use this as a basis for determining the right strategy for concrete mixture design. Now, alternative cements, I said, you have, of course, alkali activated systems where alkalis like sodium potassium hydroxide are used to activate polymerization of aluminosilicate materials like fly ash or calcined clay, right? Or in case of slag, you do alkali activation of the hydration of slag. You produce slightly different systems with both of these approaches, but yeah, ultimately you're working in a system without any Portland cement. Now, calcium sulfoaluminate belite cements, again, in China, these are really big. The idea is that you produce cement at a lower temperature, right? With the right kind of approaches of selecting the right raw materials, and overall lower carbon dioxide emission happens in this process. The only problem here is the alumina sources that you need to look at are quite expensive, like bauxite, for instance. Even to produce calcium aluminate cement, the bauxite could be very expensive as compared to limestone. Magnesia-based cements, I already talked about. These are essentially cements that absorb CO2 over their life, and then the net CO2 becomes negative. Wollastonite-based cement has also been used. Solidia is a company in the US that came up. It used carbon dioxide curing to convert the wollastonite-based systems into CSH and calcium carbonate. Now, unfortunately, many of these companies that looked at these alternate cements really did not get the right business and closed down. In fact, even companies that came up with geopolymer systems commercially did not really do that well. Although there have been some companies that have had some level of success in niche markets. Again, we have to look at the scale. Are we able to address the problems at scale? In Portland cement, we're talking about 25 billion tons of concrete. Now, that's the scale that we need to look at. Are the materials that we're proposing capable of making a difference at that scale. Maximizing aggregate in concrete obviously is very important from the point of view of reducing cement, and that automatically reduces your CO2 impact, right? How do you maximize aggregate? One strategy could be particle packing. This is a concept that we borrowed from the powder metallurgy industry, where they look at particle distributions and then optimize them so that the material can get the best solid packing without much voids in the system. So particle packing is an approach which could be followed. It's a very simple approach to follow for mixed designs, brings about better economy. And of course, because you're having greater amount of aggregate in your system, it gets better dimensional stability. Now, this example from Sweden and the bridge tunnel system connecting Sweden to Denmark between Copenhagen and Malbo. This has a tunnel, dredging and reclamation and a bridge. It was designed for a 100-year service life. And note that all of this was done at total cementitious contents of well less than 450 kilogram per cubic meter. Here, they had used the particle packing system to bring down the need for large amounts of cement. Because obviously, structures are going to be massive. If you put more cement, there's going to be a lot more heat generated. You want to avoid heat-related problems. So this is one possible way of actually reducing the extent of cement, increasing the aggregate content, get better dimensional stability, reduced heat, and still produce concrete that is highly durable. Now, the other approach to really ensuring durability is to adopt what we call as performance-based specifications. To give the simplest example of a performance specification, you walk into an electrical shop, you want to buy a bulb, you don't look at the wattage, you don't look at the size of the tungsten filament. All you do is you get the shopkeeper to put this in a socket and turn the switch on, it works. That's a performance specification. In concrete, unfortunately, there are no easy ways to do that. But what one of the leading scientists in concrete, Doug Hooton, says, you can introduce a scratch and sniff test when the concrete comes, scratch it, sniff it, see if it's okay. But that was just a joke. Primarily, you can look at simple parameters when the concrete truck comes into your site, is something called a water content determination. Because you know often that to increase the slump at site, a lot of people end up retempering, adding water to the concrete, which is obviously not good because it's going to compromise both your strength and durability, right? Can we have a simple test in which we measure the water content? That could be a simple test that we do on the site. That's a performance specification. Can we write a spec which says when the concrete truck arrives at site, you take a sample and determine the water content? That could be a simple test similar to the electric bulb kind of thing. All right. So what we've been currently following, obviously, are the prescriptive requirements. We say that, okay, in this environment, use this material, use so much of this, use at least this grade of concrete, and you'll be fine. But what it doesn't seem to touch upon is how is this concrete being put in service? What are we doing in terms of compaction, curing, workmanship? Are we paying attention to the initial concrete temperature? Can we then start looking at bringing those things into the specs and defining what is the performance that we need? And that's what is called the performance approach. So just to give you an example, of course, when prescriptive specifications can include curing duration and method, say 7 days curing by water fogging or ponding or something like that, you say that minimum cement content should be so much, maximum water cement ratio should be so much, you have to use only this type of binder. Those are prescriptive specifications. A performance means you are having a measurable parameter that you're defining. Now, interestingly, in many of your specs, you would have already seen cover depth as a prescriptive spec. It'll say that for an extreme exposure environment, use 75 millimeters cover depth, right? What can we do here to make it a performance spec? We actually measure that cover. And measurement of cover is not that difficult. You have cover meters available, very cheap for construction sites, not a problem at all to actually get these cover meters. Determine cover, not on all the elements because that will put off your project by several months. You want to do it on some selected elements to ensure that people have been paying attention to actually doing the right job with performance specs. Now, I often joke that when we enter hotels in India, we have this metal detector. Doesn't matter what you have in your pocket, it always beeps, right? Maybe in a construction site, we have one of these large detectors. When the truck arrives, it beeps. It gives the contractor some idea that, okay, somebody's checking something that I'm doing, right? Maybe that would have been a good idea to increase durability on construction sites. Now here, performance spec example is the new Panama Canal, which was looked at to determine what would be the control of the concrete quality on site. So here what they did was they established the concrete quality that is needed in the lab as 1,000 coulombs of rapid chloride penetration. And they correlated that with a field-based test, that is the resistivity measurement. And they found that for a certain level of chloride penetration, this is the resistivity that I want to have in the system. They use the resistivity to actually measure the parameter directly on the constructed elements. So look at this. We don't have to rely anymore on lab specimens. We are actually measuring directly the durability on the site. Of course, there are issues with using resistivity directly because you need to be aware of the moisture conditions, presence of reinforcement, several issues are there. But if you play within the confines of what this can do, then you really have an approach which can be utilized to determine durability of constructed elements. Again, an example from Doha Metro. This is an L&T project where they looked at different types of concrete elements in the same metro construction project. You had concrete in contact with the ground, concrete not in contact with the ground, and high-strength concrete for internal columns. So obviously, we know that when concrete is in contact with the ground, we need to have protection against chemical attack. If your ground has sulfates or chlorides, concrete not in contact with the ground, there's obviously going to be carbonation, right? So the tests that were prescribed here to be done on the concrete and the limits that were done were to ensure that the durability performance in those environments will be perfectly satisfied. Alternative aggregates, I think you'll have a lot more discussion later. I'll probably just touch upon briefly. You have manufactured aggregate, which is from industries, or construction and demolition waste, where you actually crush the demolished concrete and utilize that as C&D waste. Now, the challenge obviously is, again, do we know where it is available? Is there a good spread? Can we arrive at a proper understanding of the logistics? Do we need to process and remove unwanted material? And what is the cost and energy impact of this processing? Is that going to induce more cost, more energy, more CO2? That has to be perfectly calculated. Sometimes, of course, processing demands a lot of energy. And what is the long-term stability of many of these materials? Are they going to be stable in the long term? Because concrete we want to serve for a very long period of time. Do we have that level of stability from these materials? And for recycled aggregate, how to work out sustainable method for processing. Again, sustainability framework is very important. We need to look at all the possible operations that go into actually utilizing demolition waste, calculate the CO2 and energy impacts, and then evaluate whether the system is actually working for us or not. One example of work that was done by my colleagues, Professor Gettu and Professor Surender, is to look at using concentrated solar to break down the mortar from the aggregate. And using this process, they were able to supply sufficient heat for a thermal beneficiation and later crushed to obtain perfect aggregate, fine aggregate, and recycled concrete fines. So this approach is something that needs to be scaled up. We are still looking for possibilities with which we can scale this up. This was done at a facility in Mount Abu in Rajasthan. And CO2 curing reabsorption, I'm not going to talk too much about it, but yeah, several alternatives are based on net zero CO2. Again, the issue is this science is still at a nascent stage. A lot of people are making a lot of big claims about it. My suggestion is take everything with a pinch of salt. We need to analyze these systems very carefully. They are not really all that they seem to be, okay? The opportunity, of course, is that you have concrete block manufacture for unreinforced concrete elements, which definitely can benefit from many of these strategies. Right. Okay, the bigger picture, materials obviously is only one part of the story. There's a lot more to be done to make structures sustainable. The process obviously is extremely important. You need to look at what is the overall process of putting together your structure. And as I said, today's emphasis, if you look at the way that electrical systems have been designed, appliances are being designed, people are looking at lowering the operational CO2 and energy. We also have to pay attention to embodied CO2 and energy, which is why understanding the material characteristics is absolutely important. And policy also needs attention. One example, again, use of construction demolition waste. There are places where natural aggregate is available much cheaper than C&D waste. So why should the contractor bother with choosing C&D waste when they can get natural aggregate? Unless there's a policy that drives it. For instance, in Singapore, they allow 20%, they mandate that 20% of your concrete has to have recycled aggregate in it. So that's a mandate if that puts a strong policy in favor of actually using C&D based systems, irrespective of the cost. So obviously, this needs a concerted effort across different time scales, different scales of study. So we have set up a very large center. Tomorrow, I'll talk about this in the workshop. This is the Center for Technologies for Low Carbon and Lean Construction. Somehow that, okay, maybe it indicates that my time is up. So thank you all very much.
Thank you. I want to thank you for the inspiring presentation. It was wonderful to take us through many strategies, many challenges, and also opportunities in space of decarbonization of concrete, which is going to be, especially for the young generation here, a wonderful era to bring engineering again in a real role in society. You know, nowadays we're all looking at smartphones. Decarbonization is going to affect everyone, so no matter what, you've got a smartphone. So, any questions? Any questions?
Thank you.
So one question is, as we use more of fly ash, GGBS, all these materials are byproducts. Is there any research in the long term, not the performance of the structural strength, durability, health effects? How comfortable are we? In US, there were a lot of lawsuits.
Okay.
Long-term indoor air quality and its effect on health. Is there any work going on here in India as well and other places?
No, that's one aspect that's not been looked at in detail. And that's, you bring about a valid point, because very often in our zeal to reduce the dependence on natural materials, use more waste and byproducts, we end up utilizing a lot of materials that potentially could be hazardous to health. Especially, there's a lot of talk about using plastic as a material to replace aggregate, or even to crush it as a powder and put in concrete. What are the long-term ramifications? Because in an alkaline environment, some of these may actually break down and release some toxins. With fly ash and slag, there is not really much documented. Only in case of fly ash in embankments, the leaching due to water sometimes brings out more heavy metals. But in concrete, many of these heavy metals get immobilized. So usually, I have not seen any adverse effects there.
Can I follow up with just a small question? So I think, see, asbestos is banned everywhere. In fact, that's the best material from fire resistance point of view and other things.
Correct.
Similarly, by using all these materials, I think there should be a concerted effort, long time. What's the effects on it? Especially, India may not be that bad. In US and Canada, where we don't open up windows or, you know, for
there's no natural ventilation.
Yeah, natural ventilation. So that, I think, there were lawsuits in the US. I don't follow that. So in fact, that's one of the reasons why it has been.
It's a very valid point. I think we should look at that.
Your center, that's my recommendation.
Maybe that could be a new line of work. Sure.
Sir, the construction and demolition waste.
Yes.
Are there any studies done for the cost effectiveness apart from the energy utilization for breaking down the materials?
Yeah, so cost effectiveness, of course, has to encompass the overall processing of the material also, breaking it down into aggregate size, if necessary, removing the mortar before reusing it, or using it just as a crushed material. In that case, you have to do a little bit more optimization of the mixed design strategies. So it's not very easy to pin down exactly the cost. It's not just the cost of crushing. You may have to readjust your concrete mix design to suit this material to be used and so on. But yeah, there is sufficient information available through research and through practice that can help us help to guide in this direction.
Thank you. Maybe we've got time for one last question. The question is coming soon.
You can speak out, no problem. I'll repeat your question so that everybody hears.
In UK and Europe, we are now looking at the carbon capture storage. So instead of obviously we know concrete has performed over
Yeah.
hundreds and thousands of years. And as Professor Kodur said, fire is also obviously very much proven technology in those. Are we in India, are we looking at the carbon capture storage where we can actually decarbonize it, right?
Sure.
Because in the UK and Europe, the suppliers are investing a lot of money to carbon capture storage.
Yeah.
Yeah.
Yeah, good that you brought up that question. There's a lot of emphasis on carbon capture and storage now. In fact, recently the Department of Science and Technology also initiated a research call on CCU in the cement sector, and they followed up that with a cement CCU call in steel sector. And there are a lot of approaches that have been already put into place in terms of developing carbon storage type facilities, both on amine absorption and solid sorbent adsorption process. There's also the issue, of course, that, okay, after you store, do we have a way to actually get it in a place where it will not come out again? Or can you use the stored material to mineralize? And that's where actually our group is also working for one of the DST projects that we are doing. Basically, we are looking at, can we use the CO2 which is stored to also mineralize cementitious materials and reduce the need for finding ways to store this? Yeah, but definitely efforts are on at different scales, especially in the industry. There's been a lot of effort to actually reduce CO2 emissions.
Professor Santaman, thank you very much for the
Sure.
presentation.
My
Really
pleasure.
enjoyable, and also for the question time.
Thank you.
Very entertaining.
Thank
Thank you. Wonderful. We can now move to the next plenary talk. It's a privilege to invite Professor Martin Menzinger, Chair of Metal Structures at the Technical University of Munich, TUM, well known as TUM, to the stage. Professor Menzinger will be speaking on the topic buckling behavior of longitudinal Stephen plates under biaxial loading, recent research at TUM. And it is an honor to welcome Professor Martin Menzinger, Chair of Metal Structures at the Technical University of Munich, a distinguished expert in steel and composite construction. Professor Menzinger has significantly advanced research in plate buckling, fatigue, fire and explosion protection, and the structural assessment of historic steel infrastructure. He's a certified expert and consultant for railway structural safety and plays a vital role in revising European standards such as the Eurocode 4 and guidelines for historic steel structures. Through his academic leadership and consulting expertise, Professor Menzinger bridges research and real-world engineering practice with excellence, which I must say is very important when you work in academia. And from my personal interaction, brief interaction with Professor Menzinger, I must say he's very passionate about sustainability, both at a technical level and also how to bring it really back in a broader community. So please join me welcoming Professor Menzinger to the stage.
Thank you, Gianluca, for this nice introduction, and good morning to everybody. First, I want to express my gratitude for being invited to speak to you. And for me, the last day were very, very nice. I experienced an unbelievable hospitality, which I didn't expect it in that great. And many thanks to also organizing team, and especially to the students who are really very eager to support us as much as possible. Okay, and sorry for missing the dancing last night. So we went home to the guest house too early. Today I will speak about the buckling behavior of longitudinal stiffened plates under biaxial compression. This is a topic from steel construction, so I recognize many of you are dealing more with concrete, but perhaps also a short lecture about steel is something inspiring. And I try to use this device, but it's at the moment it's not working. Perhaps this way. Okay. Okay, so here's the outline of my presentation. I will give you a short insight into the motivation of my research and also about current design worlds in Europe and Germany. And then I will proceed with our experimental and numerical investigations. And at the end, I present a approach for considering the eccentric load introduction in the buckling analysis according to Eurocode 3 part 1.5, which is a code whose rules the buckling design of plate buckling, which of steel plates, which is relevant for the construction of steel bridges. So let's talk a little bit about my motivation and for this research. This is also related to this nice bridge in Nuremberg, which we are just finishing now at the moment. We have to say in Germany, we face the situations that we have an existing infrastructure. So our railway bridges are about 100 years old, some of them even older, and the highway bridges are about 70 to 50 years old at the moment. And we have to about 36,000 railway bridges in Germany with about 80,000 superstructures and also about 40,000 highway bridges. And we have to replace several thousands of them in the next years. And this is a difficult task to do. So and many of those bridges are replaced by incremental launching, because the advantage of incremental launching is that you don't have to disturb the traffic. So, and the largest bridge where we used incremental launching in Germany was a Hochmosel crossing with a maximum span between the pillars of more than 200 meters. Unfortunately, I was not involved in this project. I would have loved to be part of it, but I wasn't. And you see, the auxiliary pylon was used to be able to bridge this large span during the incremental launching. Other examples, which are more typical, are bridges with about spans between 100 and 120 meters. This is a range where steel bridges are economic in Germany if we use incremental launching. This is, for example, a bridge close to Würzburg with a span of 120 meters, or also at the moment under construction, one of the largest bridges in Germany, the Rader Hochbrücke. And you see there quite a high number of bridges launched at the moment because of the benefits. It's an economic solution. We can prefabricate the bridge segments at the assembly area on site. We are also able later to launch the bridge. And as you can see here in this example with this flyover in Nuremberg, we launched this bridge with a total length of 650 meters without one-day traffic disturbance. So during the whole construction time, the traffic of the highway close to Nuremberg was not disturbed, and it would also not be possible to accept a disturbance of the traffic for such structures. So this was a bridge where I was a check engineer, so it was really fun to build it. By the way, it has nothing to do with science, but it's also nice. And this is a typical example of a box girder, how we construct them in Germany. Normally, we are using trapezoidal stiffeners. We have steel webs and a lower flange made of steel. And in case of the bridges with spans around 100 meters, we are normally using a composite deck, not a pure steel deck, as it was used for the Hochmosel viaduct. And during launching in the web and also in the bottle plate, we have to face biaxial stress plates, because we have this hogging bending moment at the pillar, which causes stresses in the X direction, so the longitudinal direction of the bridge. And we have also the introduction of the bearing forces into the web, which also causes vertical stresses in a Z direction. And also the bottom plate is stressed with biaxial compression from the bending moment, from the inclination of the webs, and additionally also from the shear flow at the support. So we have to design those plates against buckling under biaxial stresses. And in addition, this design check is normally ruling the size of the thickness of the web plates and the bottom plate. And therefore, it's really essential also for a material efficient construction to optimize those design checks. And during erection, we have in two different sliding systems we are using for launching. One is a well-known rocker bearing, which is shown here in the case of the Lichtenfels viaduct, which is also a bridge we have under construction now. And other companies prefer to use hydraulic checks and in addition a spherical bearing. And those two different systems of launching devices are influencing the buckling behavior of the plates, which is not covered by the codes up to now. At the moment, the codes just recognize in-plane forces, but no bending moments from eccentricities. And those bending moments from eccentricities are influenced by the launching device which is used. And there are significant differences. And that was also one of our major things we focused in our research. And then we have also mixed structures This is Elbe-Brücke Wittenberge, bridge over the Elbe at Wittenberge, and this spherical bearing here in the middle has to bear a load of about 40 meganewton during launching, so really heavy loaded bearings in use for that. Okay, now let's talk about those different bearing systems. And the big difference is a degree of freedom here around the longitudinal axis. So in case of the rocker bearings, we can allow only a behavior like that in the longitudinal direction of the bridge, but we don't have this degree of freedom around the longitudinal axis as we have it in the spherical, in case of the spherical bearing. So we have a total different bearing conditions, which is not considered in the buckling checks. We were interested, how do those bearing conditions influence the buckling behavior of the web plates and the bottom plates of our bridge. And also we have always to recognize some eccentricities. We have eccentricity by design because the thickness of the web plate is changing, and therefore the center line of the web plate is also changing. We have to also to allow some eccentricities just for practical purposes, and necessarily air gap to the lateral guidance of the bridge. And in addition, we have probably some tolerances from erection we have to consider. And all those eccentricities are also ignored in all the design checks at the moment. Okay, how to avoid it? A good engineer always tries to avoid any problem. So simple constructions are mainly the best one. And one simple trick to avoid is, for example, is to add some cross beams between the launching devices in case of the spherical bearings, and then we don't have to think about any eccentricities anymore, because all the moments from eccentricity will be beared by the launching device and will not be introduced into the web. So this is only possible in certain cases, for example, the Saale crossing Salzmünde, and also again this bridge over the Elbe, where we used this small trick to avoid discussions about the buckling check. But normally you don't have the possibility to do that. And we therefore tried to further develop the design check according to Eurocode 3.15. And you see there was quite a high number of changes in the last years. My presentation deals mainly with a version of Eurocode 3.15 from 2019, and now there's a new one available already since April. So there's a continuous change. Also, some wording is changing, which makes it difficult perhaps to understand everything, but I try to do my best to explain. And Eurocode 3.15 in general provides two different methods for the buckling check of panels. One is effective width method, which is used in UK and also in France. And there's another method, which is the reduced stress method, which is preferred in Germany for bridges. Both have some advantages and some disadvantages. The advantages of the reduced stress method is that you not only can design rectangular panels, but you are free in your form, and you also you don't have to change the section values, which is very beneficial, especially in the case of incremental launching, where you have quite a lot of different construction stages, which would lead to quite a high number of different section values you have to consider if you apply the effective width method. But this is discussable, so preferences are more national and scientifically based. So, but in Germany, it's also mandatory to use a reduced stress method for bridges in Germany, and that's why the reason why we focused on this method. There's also a possibility to design the buckling set, or to perform the buckling checks by using the finite element model. So with finite element models, there were some in Annex C of Eurocode 3.5, you can find some recommendation for the imperfections, but those imperfections were not validated. So there's no big scientific background on this. Imperfections or no scientific background could be found. And this Annex C will now move in future to the new part 114 of Eurocode 3, which deals with numerical method in the design of steel structures. Okay, coming back to the reduced stress method. So the design check with this method is performed with a formula which is more or less based on the well-known formula of the yield criterion from Huber-Henke-Mises. So if you look at this formula, it has exactly the same format, but additionally to the formula was a yield criterion. We added these reduction factors, rho Cx, rho Cz, and so on, where we consider the buckling behavior. And in these factors, they are we consider as well the buckling behavior for plate buckling and also the behavior for column-like buckling. So rho Cz and rho Cx are determined in a two-step procedure where we firstly determine the reduction factor for pure plate buckling, and then we check if there also column-like buckling may occur, and then we get those factors. And I will talk a little bit more about these factors. And some years ago, this factor rho V was newly introduced. It formerly is called V only, but now it's called rho V. This is one of the things which changed between 2019 to 2025. And this was necessary because of this mixed term with the stresses sigma x and sigma z, and because in case of yielding, it is positive if we have compression in x direction and also in z direction. But it's exactly vice versa in case of buckling. And in case of buckling, it's unbeneficial if we have compression in both directions. It's very obvious, and we can't directly use a yield criterion for Huber-Hanke metres for describing buckling. This is one major point which is criticized on this method. And to heal this mistake, this factor rho V was introduced some years ago by Ulrike Kuhlmann. But in the time between 2003 and 2015, quite a high number of bridges were built without rho V, and nothing happened. So there was no accident, and therefore it was questioned: is it necessary to introduce rho V? From a mechanical point of view, it is necessary, but it is discussable if it's also necessary from the safety level we reach with this design check, and therefore this was the start of our research. And just for your better understanding, those reduction factors rho are derived by using a related slenderness, lambda p, and the related slenderness for the calculating the related slenderness, we are using two factors and something like a global buckling value alpha British. So the procedure is the same as it is normally done for buckling checks for columns and also for lateral torsional buckling. So the procedure for plate buckling is exactly the same. But with these values, we are using all stress components in one factor. And this is a difference to the effective width method, where we are using only the components stresses for the buckling stress for each component, for each single component. Now, this is again an advantage of the reduced stress method. This is more closer to reality. Okay, and the other research question was not only if rho V is necessary, but also there was a discussion about the consideration of the torsional stiffness or of longitudinal stiffness. And also the question was, are the imperfections of Annex C, are they on the safe-sided or not? And also, in my opinion, most important question, how do the different launching systems influence the buckling behavior of those plates? So this is another bridge I visited with my student last week before I moved to India. Also, this is again a large bridge which is constructed by incremental launching. And we had exactly the same discussion about the introduction of the load eccentricity with this bridge. So we at Munich, we were allowed to perform some nice experiments with this new developed test setup. And I will talk a little bit about that later. And also we were allowed to perform some measurements of imperfections at another bridge, which is the Talbrücke Tulpa, the Tulpa viaduct, also typical composite bridge with spans about 100 meters or a little bit more. And some information about this bridge. So this bridge has, oh no, it has less than 100 meters and only 90 meter span. total length 460 meters. This is finished now, and it's also a typical box girder, composite box girder, as we use them in Germany. So in this particular case, we don't have an upper steel cord. Sometimes we are already during ease of erection, we have also an upper steel cord and then a composite slab above it. In that case, with a little bit more material efficient, we have a pure concrete cord which is connected with hessian studs to this U-shaped steel section during launching. And we performed with laser measurements, some measurements in 3 segments of the bridge, and measured the deformation of the web and of those web panels during the erection of the bridge in different phases. So here is a bridge. So this is the launching nose, and then we have the different segments of the bridge, and we were able to measure 3 panels, and we did several measurements. We measured at daytime, in the night, and then during launching, when those webs were located more or less at midspan, and another case where they located above a pillar, where we had also this cross-directional stresses from the bearings. And here you see just a small figure of that. And the interesting result is on this slide. You can see the assumption of Eurocode 3 part 1.5, which is a gray line, are safe-sided. So there's good news. And we also found out that they will lead to pretty realistic results compared to our tests later. And this is therefore the imperfections which are defined in Eurocode 3 part 1.5 can really be used for finite element calculation of the load-bearing capacity of those panels. Now let's come to the buckling tests. The buckling tests were performed by Nadine Thomas. Nadine is a postdoc at my chair now. At that time, she was one of my PhD students, and she is a young mother with a baby of 1 year. So a little bit like Monica, the same living situation. And she was able to, she performed in her PhD student studies these buckling tests. And for that reason, she developed, with a little help of mine, this test setup, which has a span of 11 meters, 7.5 meters high. This is high-strength steel. Also, blue parts are high-strength steel. And we were able to perform tests on web panels with a size of 4 to 3 meters. And we were able to apply a bending moment of 34 meganewton meters and a cross-direction load of 8.6 meganewton. So we are not in the range of the real bridge, but we are pretty close to those web panels, which is essential if we want to consider especially weld imperfections in the right way. Because if we are choosing the web panel too thin, we will have different web deformation and imperfections due to welding than we are compared to realistic structures. That's the reason why we built this big tests set up, and we were also looking at the different bearing systems. So we performed 4 tests with hydraulic spherical bearings, and also 8 tests with a more common rocker bearing. So we were able to simulate that with this load introduction device. Here, you can see it here. This is a spherical bearing, and here we have this rocker bearing. You can easily see the differences. During our first test, we applied the longitudinal load in the first steps in X direction. This is the force F1. So the bending moment was introduced first, and after that we were introducing the normal force in the longitudinal, in the cross direction, which is not happening like that in real structures. In real structures, both occur simultaneously, but we feared that something will happen because this is a dangerous test. It's a large test with really high forces, and so we were a little bit cautious. That's the reason why. And later on, we checked if this load sequence has an influence on the upper load limit, and I will talk a little bit later about that again. And also, we measured again the initial imperfections of our test specimen by laser, via laser, and we used quite a lot of other measurements like inductive placement sensors, strain gauges, optical fiber we also use. I will not talk about that here because for us it's more interesting to see, to have a look at one test. This is one typical test specimen, and what you see here, and this is something what I would like to ask you to have a focus. We here at the beginning we saw that in this local buckling field, the first buckling field, initially due to this load introduction of the X-force, we introduced a multi-wave buckling pattern, and this buckling pattern in the next step acted as a stiffener for the cross-directional load. So if we have a multi-wave buckling pattern in the first buckling field, we will increase the bearing capacity for cross-directional loading. And exactly that happened in this test. I hope you saw it, but we see it also later on a laser scan. Okay, we varied, and therefore it is important how it's the relation of the stresses in X direction compared to the stresses in Z direction, because in the stresses in X direction might lead to this multi-wave buckling, which then enhance the bearing capacity for cross-directional load. And therefore, that was one reason we varied this in our tests. We kept some parameters constant, but in overall we had a lot of variations. And we during our tests we observed 3 different failure modes. So we in some cases we had buckling in positive Y direction. So this is the direction here up in the direction of the stiffeners. And this is the case when the longitudinal stress is dominant and the cross-directional stress is small. In case that if the cross-directional stress is dominant and the longitudinal stress is small, we will have a failure in negative Y direction, this direction. And sometimes, as in the test we just observed with a short video, we have this situation that we have this multi-wave pattern in the lower buckling field, which stabilizes the panel and will help to increase the bearing capacity in cross direction. I'm not sure if we should consider that in the real design, because due to welding imperfections, we may have the situation that in certain cases, this pattern will not occur in reality. This depends on the welding imperfections. Yes, and this is something which we should keep in mind and also discuss critically if we should accept that. Now let's have a look on the and compare the test results with a design approach according to Eurocode. And what we found out is that we are always conservative with the Eurocode design, even if we neglect the new introduced value rho v. We are always still safe-sided. So the blue line, the blue column is with rho v, and the green one without. And this is a quota between the test result compared to the design according to Eurocode. And so even without rho v, we are safe-sided. Okay, and some our findings are I think we should consider rho v from a mechanical point of view, but we should discuss to lower the overall safety level. And also we should neglect the torsional stiffness of the trapezoidal stiffener. And also in addition, we found out an additional design check against just normal column-like buckling of the stiffener would enhance the accuracy of our design. Yeah, so which is not necessary up to now. Okay, let's move to the numerical investigations. What we did, we also considered the 2 different types of bearings in our numerical campaign, and we used for the numerical calculations different approaches. One approach was using the first buckling mode and calibrating it with values from imperfection from the measurement to recalculate our tests. Another was using the overall imperfections and also using combined buckling modes for the calculation of the buckling fields. And this was done with several master theses from Julian Seisenberger, for example, he was looking mainly at the superposition of several buckling modes, and we found out more or less using the first buckling mode is okay. And also, again, the effect with I already explained that we have this positive effect of multi-wave buckling in some cases. Then we were discussing the influence of the load sequence, and this was done by Alexander Stary, and we found out in that case that it has no influence to the ultimate load, but allows us for better understanding for the behavior of the test specimen during the test. So we had a change of the sign of the deflection. So at the beginning, the test specimen moved down, and later on it moved up again. And by considering the load sequence, it is possible to calculate this load-bearing behavior, but it's not necessary for calculating the ultimate load. And again, also using the measured imperfections from laser scanning will just lead to this more or less the same result. So also using the first buckling mode is a good approach, also compared to our measured results. And what we found out in all our calculations are that we a little bit overestimated the load-bearing capacity compared to the tests with our numerical calculations. And this is because I think we are not able to perfectly define the load introduction eccentricities of the load device, because in the load stays at the same height and the specimen moves up and down a little, and this is really difficult to simulate. Yes, and I think that's the reason why we were not able to have a perfect fit from the numerical simulations to the tests. Okay, and if you look again at the reduced stress method, we are also able to recalculate the stresses of our test specimen just with a simple approach, and then we are able to calculate the design according to Eurocode 3 with our results from our numerical simulations. And we did that for a quite high number of geometries with in frame of a parametric study. And what we found out is that in that case, that the Eurocode is very conservative compared to our numerical calculations, even in case of spherical bearings, but only to a certain degree of eccentricity. If we have a larger eccentricity, larger than 30 millimeters, we will really have a problem. So that the design check as it is now will also come to the unsafe side. And if we are able to limit the eccentricities, in the same time, it will be very much on the safe side. For me, in my opinion, there's a need for discussing to further develop the design check. And in case of roller bearings, we are just very conservative. So you can see here, so we are able to, in our stresses we can take about 250 megapascal, and according to Eurocode 2 in that particular case, it's just an example, it's only less than 150 megapascal. So in also the frame of optimizing structures, also for sustainability, minimizing material consumption, we should discuss if this design check is not too conservative. Okay, that's why we are trying to introduce a new coefficient omega, when we derived this new coefficient omega with just a simple engineering model, very simple, just springs and torsional stiffness is needed, and a numerical calibration factor K, which is also introduced, and we are introducing this in this formula. And then we can also use this factor omega to also introduce the different launching devices. We can have a different omega for spherical bearings, and as for roller bearings, this also allows us to implement realistic support conditions into the buckling check. And we did also some probabilistic things in order to verify if we are on the safe side, and that's led to the definition of the calibration factor K to 0.7. And this again, in case of the spherical bearings, we will now have a conservative, still compared to the numerical simulations, conservative approach, but which is also able to consider the eccentricity of the load introduction from this eccentricity resulting bending moments in the web panel, which is not possible up to now. And in some cases, we will also see that we have to increase the web thickness or to limit the eccentricities for our bridge. And I think this is a big progress, not only for economy, but also for the safety during launching. And this is a simple formula for the spherical bearings. We recommend omega with this nice formula, factor 0.7. And in case for launching rockers, we recommend that omega is also a fixed value 0.7. So we just lowering the safety margin of this the design a little bit in order to allow more economic and therefore also more sustainable construction in this field. Okay, that's it. I hope I'm still in time, which is not easy in case of a complex topic, and I'm well known in Germany for not keeping my time. So today I really did my best. And thank you very much for your attention, and I'm open for questions.
Professor Menzinger, thank you very much for the enlightening presentation. I think it was a wonderful example of bringing the elegance of the mathematics, the structural mechanics that goes into our codes to a real application. And I think also for hiding all the difficult aspects of the modeling and the experimental part, which I think are certainly not trivial, but you make us look as very simple to do. So it's a real pleasure to see. Any questions? Please. Let's go.
Sir, you have mentioned, well, launching by incrementally, these stiffeners are very much useful, longitudinal stiffeners.
Yes.
But in service, are they useful?
Yes, also in the service, we need a longitudinal stiffeners for those steel plates. And we because we will also have positive and negative bending moments, which will lead to buckling of our simple plates. You have to recognize that the plates, the web height is, in the cases I presented, normally between at least 3 meters, but up to nearly 7 meters. And if we would design only plates without stiffeners, we would face plate thicknesses up to 60 to 100 millimeters, and we try to optimize it. So if, for example, in the Heidingsfeld viaduct, they started with 60 millimeter web thickness, and we were able to reduce it to less than a half, just by more sophisticated design. And this is all for not only for the owner of the bridge a big issue, because it's steel is not cheap, and but also from CO2 production. I think we not only have to reduce the CO2 of our materials, but we also have to reduce the material consumption. And I think in case of steel structures, we have at least 25% possibility reduce only by good design the CO2 footprint of our structures. This is the challenge for all of us. Yes.
A question about the erection. Usually the plates will be produced in a factory, and then it will be transported on site, and then welding work will come, and so on and so on. How do you ensure that the imperfections will remain the same, or how will you make the quality control on site?
Okay, so I think we have the situations that we have shops, steel contractors. Normally they produce segments in a size they can handle about 100 to 160 ton segments, but normally the segments are here in that case it's transported on the road, and therefore they are limited to perhaps 30 tons, 40 tons. And then and there's always a concept for the prefabrication in the shop, and then they are welded on site, and this is supervised with continuous measurement. And also there are the owner normally has consultants who is only for supervising welding quality and geometry of those bridges.
Maybe one last quick question, because we're just we started a bit late.
So in China and other places, Far East, the steels which are using is 690, 960 grades are being introduced. Are there any local buckling requirements? Because they will buckle very quickly.
Yes.
E won't change, FY will change. So is there any provisions in Eurocode you are thinking of putting forward? Right now, there are none for.
Yeah, so that's really a good question, because in Eurocode 3, not Eurocode 4, switched from S700 to S460 as a highest steel grade to a yield strength of 700 megapascal. And and I was responsible for Eurocode 4 in some parts, and we did not make this step because there was a lack of research. In case of composite structures, we have also an interaction between concrete and the maximum concrete strain, for example, with a steel structure. Therefore, in my opinion, there was not enough research just to say, okay, just use a higher steel grade. And that's the reason why we were a little bit conservative. Probably that's wrong, but I think research should come before coding and not afterwards. And in case of bridges, we are normally using just S355 and in some cases S460. The application in bridges for S690, I think I see it a little bit critical because this will cause not buckling problems. So I think we can cover that with our methods in that case, but we will have a loss of robustness and we will face major fatigue problems, especially if we have the traffic light on the highways in Germany. So I think, and we try to design our bridges also for a lifetime of at least 100 years. And my father built bridges also for 100 years, and all of them were removed after 50 years. So we try to do it in a manner that they will last from our today's knowledge for 100 years. But things are changing very quickly from decade to decade, especially traffic loads. So we will never know that, and therefore I would not recommend to build not robust. I think it's a good investment to use a lower steel grades and to perform a detailed fatigue design in order to have to be able to run the bridge over several decades.
Thank you very much. And I think just mindful of time, I would suggest the remaining questions to maybe be shared with the presenter during the tea break. And thank you again, Professor Menzinger, for the presentation.
And thank you for your attention.
Wonderful. As the next, we have a talk by the RILEM Youth Wing presented by Dr. Surendra Singh, Chair of the RILEM Youth Council. Dr. Surendra Singh is an associate professor in the Department of Civil Engineering at IIT Madras, specializing in transportation engineering and sustainable concrete pavements. He earned his BTech from DC Rust, MTech in pavement engineering from NIT Kurukshetra, and PhD from IIT Roorkee, where his work focused on the use of recycled materials in concrete pavement construction. Since joining IIT Madras in 2019, Dr. Singh has received multiple prestigious honors, including the IIT Madras Young Faculty Recognition Award in 2023, the INAE Young Associate Award 2023, and the Institute Research and Development Award in just last year. His research group is actively advancing eco-friendly construction techniques, particularly the use of recycled aggregates and circular economy practices in pavement design. Dr. Singh currently serves as chair of the RILEM Youth Council, where he leads global efforts to promote youth participation in technical committees, educational outreach, and leadership development within the civil engineering community. Please welcome me and join me in welcoming Dr. Surendra Singh. Thank you very much.
Thank you. Yeah, thank you for the introduction. So today I'm representing RILEM here. I think RILEM doesn't need any introduction. This event is also one of the sponsors is RILEM. I'll just in the next 7 and so minutes, I'll just introduce you about the RILEM, its main activities and important highlights. So it's a non-profit organization which was founded in 1947 by the directors of different laboratories on construction materials, with a vision to give a platform where people who are working in a similar domain can come together, join hands, and build sustainable infrastructure. With the goals of RILEM are different goals actually, but the main are to promote cooperation at international scale, simulate new directions of research, and promote sustainable and safe construction. And after 75 years, the mission of the RILEM is again the same, and this mission is achieved by its members. So we have different membership, so like corporate membership and the individual membership. In corporate membership, if Let's say IIT Madras is also a corporate member where everyone came together who are working on materials and we took the corporate membership. But individual people can also take different membership, like such as senior member, young member, and the retired member. So if we see RILAM worldwide, we are there in almost all the countries. India is there in Southern Asia. We have around 3,400 members, 120 corporate members. And if I see the figures in the last 4 years, especially from India, the number of members were the highest, thanks to Professor Gettu and Professor Radhakrishna's initiative. Professor Gettu was the then president, and Professor Radhakrishna was the regional convener for for the South Asia region. Currently, the president of RILAM is Neil, and we have actually 4 presidents. The vice president will become the president after 3 years, and the president will become the past president. And every year we have a honorary president. We have two workshops or a conference, RILAM Annual Week. So the main coordinator of the RILAM Annual Week for that year will become the honorary president. And apart from the RILAM Week, we also have RILAM Spring Convention. So this year's RILAM Annual Week is happening in Hanoi, Vietnam. The Spring Conventional, next year it will be happening in Belgium. So as far as the organization chart, every member is having the voting rights. So whatever the decisions in RILAM we have to make, every member is holding the power. So it takes all the decisions are made in General Council, which is assisted by Bureau, Educational Activities Committee, DAC, Youth Council, and Technical Activities Committee. And the Technical Activities Committee is actually the cornerstone of RILAM. So you might have seen different technical committees that are forming. So what happens if there is a new area in which we have to work on, everyone from different laboratories, they join hands, they propose a new committee who will be working on that particular topic for around 5 to 7 years. And then after that, they'll publish the work in terms of recommendations and other things. So currently we have more than 40 active technical committees in different areas. So all these technical committees are placed in different clusters. So out of these 6 clusters, 4 clusters are pertaining to the cementitious materials. So the committee will submit or publish its the findings in terms of recommendations, proceedings, report, everything, and then most of the things are free to download. Okay, it's open access. And then we have our materials and structures journal. I think people who are working in materials and structure, they're aware of this one. It's a flagship publication. In 2016, we also started RILAM Technical Letters, which is 100% free, open access. And in 2020, it was included in the Scopus database also. And apart from materials and structures and technical letters, RILAM publishes annual reports and the technical reports. So if you see, around 47 members in RILAM are youth. So in 2020, RILAM realized that we have to include more members, youth members. So they started RILAM Youth Council. So currently, I'm heading RILAM Youth Council, and along with me, we have people all around the world. So from every region, we have one representative. For India, the representative is Professor Keshav Bhardwaj from ISC Bangalore. And we have many members, many awards for the young members. For example, Robert Lemert Medalist Award, Gustava Colonetti, RILAM Best Student Poster Award. And then for the conferences annual week, we give around 2 PhD grants, wherein the travel is covered in the travel grant. So this year's Lemert medalist is Professor Tomaso. Then we have 2 Gustava medalists. And then, coming to the educational part, so our EAC, it comes with different doctoral courses which are free to see. So we have around 140 different doctoral courses. You can register it. In fact, you can credit it. In Europe, you can credit the CPDs by watching the Rock and Talk, because the Rock and Talk is one of the most famous RILAM free webinar series. So here, the best advantage is that in the Rock and Talk, if you are working in an area and you can directly interact with the person who is who are the experts in your area. So in the Rock and Talk, we have the webinars by the expert. So 30 minutes of presentation followed by 30 minutes of live Q&A. So you can directly interact with the leaders in your area. And if you happen to miss any of the Rock and Talks, you can directly go to the RILAM YouTube channel and you can watch it for free. RILEM is also heavily engaged with the industry partners. We want to collaborate with industry. Right now, we have many corporate members from from industries. Now, coming to the last part, how to become the member, you can just, it takes few minutes. You can go to the RILEM website, you can create your free account, and you can, start reading the papers, materials and structures, or RILEM technical letters. But if you want to become a co-author of a RILEM technical committee, right now, our aim is to include more youth into the technical committee. So every technical committee is expecting to have around 5 to 7 young people. Whether they are doing PhDs or postdoc, they can be a part of technical committee. If you want to be a co-author of that technical committee, in that case, you have to take a membership. And the membership amount is very less. In fact, for the young people, we have around 27 euros, and this is without discount. If you consider the discount, for example, in India or other countries also, we have heavy discount from starting from 40% to 90%. So if somebody is there in Southern Asia part, they can get the RILEM young membership in around 10 euros. So if you have any questions regarding RILEM, please feel free to contact any of us. Thank you.
Thank you, Dr. Singh, and we thank RILEM to be our technical partner. May I kindly request our plenary chair, Professor Ranji, to please felicitate our speakers. First, may I please call upon Professor Manu Santanam. The center of assistance. Now I would like to call Professor Martin Menzinger to the stage. I would like to call the chair of RILEM Youth Council, Dr. Surendra Singh, to the stage. Surendra Singh. Please. Now I would like to request Professor Martin to kindly give a token of appreciation to our plenary chair of the session, Professor Gianluca Razdansi. Thank you, everyone. We'll have a photo session with our plenary speakers on stage. So please stay. I have an announcement for everyone. Please update or reinstall your ICCMS app. You can download your registration and accommodation invoices from the app itself. It will be updated on the app by 9th of July. We will now break for 30 minutes tea break. Please proceed to the refreshment area. Technical sessions will start at 10:50 a.m. in the respective classrooms and kindly be seated on time. At 12:30, we will gather for a group photo session, followed by lunch starting at 12:40 on the ground floor. After lunch, please reassemble to this same classroom for special talks by Professor Ravi Sinha and Professor Balhata Novak. Thank you.